Hello, this is a lecture series for Chemical Engineering Thermodynamics I. Right now we are at lecture 4B. This is part 2 of lecture 4B. In part 1, we discuss how to calculate delta S, the change in entropy, and we use the change in entropy together with the second law of thermodynamics to determine whether the process is spontaneous or not. For this lecture, we will discuss on another parameters called Gibbs free energy. At the end of last part of lecture 4B, I mentioned that for some circumstance, it would be more convenient to define new parameters called Gibbs free energy, and we will elaborate in this lecture. If, for instance, if we consider the process at constant temperature and pressure, and if in addition to this condition, if the system and the surrounding are in thermal equilibrium. The word thermal equilibrium means that both system and surrounding share the same temperature. Okay, so they are in thermal equilibrium all the way. And in addition to this assumption that temperature of the system must be constant, so that means the temperature of both system and surrounding are constant as well. Okay, in this case, if you consider heat transfer from surrounding to the system or system to surrounding, we can make a relationship that the amount of energy transferred as heat into the surrounding should be the same in magnitude as whatever comes out of the system. However, if we consider the surrounding, if we focus on the surrounding, the sign of the heat would be opposite sign to what we consider as a system. So we can create a relationship that heat of the surrounding should be the same as heat of the system, but in different sign. Okay? And at constant pressure, what we learned from lecture 2, that under the condition of constant pressure, the heat transfer of the system can be defined as change of enthalpy of the system. So this relationship from Q of the system can be translated to delta H of the systems only under the condition of constant pressure. So therefore, if we move this and replace into the definition of entropy, we can calculate delta S of surroundings from heat of the surrounding divided by temperature of surroundings, assuming that the heat transfer from the system to surroundings is reversible, just like what we mentioned in the last part of the lecture 4B, that normally we can assume that the surrounding is very, very large. The temperature of surrounding is not changing, and the process of heat transfer into the surrounding or from the surrounding to the system is usually very slow and can be considered as reversible. So under the definition of entropy change, then we can use this amount of heat as the reversible heat. So therefore, if we plug this relationship back here, we'll get the delta S surrounding equal to minus delta H of the system divided by temperature of the system. So if you notice, the right hand side of this equation are all system properties. We can represent surrounding properties by using system properties under this condition. Okay, I would like to emphasize this is true only when these assumptions are satisfied. Okay, now once we define the change in entropy of the surrounding, we can combine it with the change in entropy of the system to get delta S of the universe, because in order to use the second law of thermodynamics, we need to consider delta S of universe. So bring it here to replace it here. You can get delta S of the system equal to minus delta H of the system divided by temperature of the system. Once again, the right hand side of this equation are all system properties. So that means you can use system properties in the second law of thermodynamics if these conditions are satisfied. So let me list it again. These three conditions are constant temperature, constant pressure, and thermal equilibrium between system and surrounding. Once these three conditions are satisfied, then you can write the equation like this. That means you can use the second law from system properties only without considering the surrounding. Okay? So if I take T of the system to be just T, because temperature of the system and surrounding are the same, so I just use the capital T here and move T to the left hand side. Then I can define new variables called Gibbs free energy as G equal to H minus Ts. Okay? If you notice, H, T, and S are state properties. They're not the function of path. Okay? They are all state properties. So that means Gibbs free energy is also state properties. If I take the delta or take derivative under the condition of constant temperature, delta G of the system can be written as delta H minus T delta S. T is taken out of the delta here because T is constant under this condition. Then you can see that this on the right hand side is the same as the right hand side part of this equation. So therefore we can link delta G of the systems to minus T delta S of the universe. Once again, you can use system properties called Gibbs free energy to predict the delta S of the whole universe, and therefore we can use the second law by considering system properties only. We don't need to worry about surrounding anymore. According to the second law, the process will be spontaneous when delta S of the universe is greater than or equal to 0. Okay? If it is greater than 0, the process is spontaneous and irreversible. If it is 0, then it is reversible and spontaneous. So that means in this case, under the assumption that temperature is constant, pressure is constant, and system and surrounding are in thermal equilibrium, then we can calculate delta G of the system only and use that sign just to determine whether the process is spontaneous or not. If delta G is less than 0 or equal to 0, then the process is spontaneous. Okay? So let's put it this way. If the process is spontaneous, delta G of the system must be less than 0. When it is less than 0, it is irreversible process. If delta G of the system is greater than 0, then the process is non-spontaneous. It has no natural tendency to occur. When delta G is 0, the process is spontaneous and reversible. So sometimes we can refer to the reversible process that going back and forth between the system and surrounding as the equilibrium condition. Okay? So sometimes we use delta G equal to 0 as a criteria whether the system has reached equilibrium. But again, all these three conditions can be used to determine whether the process is spontaneous or not under the assumption that temperature of the system is constant, pressure is constant, and system and surrounding are in thermal equilibrium with respect to each other. The question would be, what kind of process satisfying that condition? Okay, what kind of process taking place at constant temperature and pressure? If you just consider a gas and you keep temperature to be constant, and you try to manipulate volume, for instance, the pressure will be changed, right? So the process that takes place under the condition of constant temperature and pressure must be some kind of specific problems. In chemical engineering, there are two main problems or two main criteria, two main circumstances that satisfy this condition. The very first one is phase equilibrium. Okay? For instance, in a boiler, if I have water heated up by using hot gas from the combustion, the red area here represents combustion gas. Okay? So the tube here is a hot tube, and the tube is surrounded by water, liquid water. So if the boiler here is operated under 1 atm, then you learn that once the water is boiled, the boiling point of water under 1 atm is 100 degrees Celsius. Okay? It doesn't matter how much water, liquid water we have, as long as there are two phases, water vapor and water liquid together, we call that state to be boiling, and that remains 100 degrees Celsius at 1 atm, no matter how much water we have. Okay? So we can say that phase equilibrium takes place under constant temperature and pressure, and therefore we can use these criteria to determine whether the phase equilibrium takes place or not. Okay? The second kind of circumstance that serve under condition of constant temperature and pressure is reaction. For instance, if I have a reactor, normally we would imagine that reaction by itself is not necessarily constant temperature. We learn that there's a reaction that is exothermic, there's a reaction that's endothermic. If it is exothermic, it is very likely that temperature of the reaction would rise up. Okay? However, in the real operation, in the chemical engineering operation, we normally prefer to control the reaction to stay at constant temperature. If the reaction inside the reactor here is exothermic, we normally provide cooling water to keep the temperature constant. Okay? If it is endothermic, then we supply heating media like steam to keep the temperature constant again. That would be easier for us to operate the system. Pressure, on the other hand, depends on the phase of the reactant and products. If both reactants and products are in liquid, we can assume that pressure of the system remains constant. But if they are gas, then normally it depends on our operation. We can control pressure of the reactor as well. So normal circumstance for the operation in chemical engineering, we usually prefer the reaction system to be operated under constant temperature and pressure. So again, this one can be we can use delta G in our advantage in this circumstance. You have to understand that these three conditions can be applied. They are applicable only when these three assumptions are satisfied. However, the G itself here, the definition of G itself, can be applied to any kind of process. Okay? So think about it this way. If you have conventional process, any kind of process, you can calculate G no matter what. But whether or not delta G would have the meaning depends on condition. Okay? It will have the meaning according to the second law only when the system pressure and temperature are constant and the system and surrounding are in thermal equilibrium. If these three situations are not satisfied, then you can just calculate delta G, and that delta G does not have that particular meaning. Okay? For reaction system, delta G can also be found in the same manner as what we did for heat of reaction. We can just find what we call delta G of formation, which is Gibbs free energy associated with formation reaction. Okay, those numbers can be found in the thermodynamics handbook or the table at the end of thermodynamics textbook. If you take delta G formation of the products subtracted by those of the reactants, then what we got would be change in Gibbs free energy of the reaction. Okay. Again, it must be the pressure and temperature must be specified. This circular sign represents standard condition of 1 bar or 1 atm, and temperature usually given as a subscript here. In addition to the application here, delta G can also be used to represent non-expansion work from the system. Okay, let me show you how. From the definition of Gibbs free energy, G is H minus Ts. If you take derivative, dG would equal to dH subtracted by TdS and SdT, because you take the derivative of the products, you get TdS and SdT. The minus sign here goes in front of these two terms. dT will be 0 if the system's temperature is constant. So under this assumption of constant temperature, dT will be 0. Then enthalpy here can also be found from definition of enthalpy that we defined in lecture 2. H would equal to internal energy plus PV. If you take derivative, you can expand this term into this equation. Again, under the assumption of constant pressure, then this dP becomes 0. If you take this dH to replace here, you end up with this equation. Okay? Now, from the first law, du would equal to dq plus dw. Again, the letter d here represents small change in internal energy, while this del in Greek represents small amount of energy transfer as heat or work. U is state properties, so change in state properties does not depend on path. That means we can choose any path that we like. If we choose the reversible path, then both heat and work must be from the reversible path. From the second law, delta S is defined as ratio of reversible heat divided by temperature. So we can change this heat into ds. If you take derivative here, if you take derivative or change delta S into derivative ds, this amount of heat will be reduced to small amount of heat. Okay, so then multiply this temperature to the left hand side. This term can be written as TdS and will be cancelled with this term. Okay, for the work, please don't jump to the conclusion that the reversible work is minus PdV, because work can be expanded into two kinds: expansion work and non-expansion work. Only the expansion work that is equal to minus PdV. So this expansion work would cancel with this term, leaving the non-expansion work here. So at the end, you see that the amount of non-expansion work within the system, or that can be extracted from the system, is equal to the change in Gibbs free energy of the system. Okay, so that's why I said that the value of delta G here, if you integrate the left hand side, you get delta G. If you integrate the right hand side, you get the total amount of non-expansion work that you can draw on from the system. Okay, once again, this would be the delta G would equal to the non-expansion work only when temperature and pressure of the system are constant. Otherwise, the whole derivation here will not satisfy this condition. The good example of non-expansion work is electricity that you can draw from reaction, especially reaction which has the electrons transfer. For instance, if I use this reaction, this is basically oxidation of a fuel. If I take hydrogen gas as a fuel and apply this to a cell, this is called fuel cell. Okay, if you notice, this is also the formation reaction for water. We discussed this reaction at the end of part 1 of lecture 4b. If we assume that this reaction takes place at 25 degrees Celsius and 1 atm and keep these two conditions to be constant, then the delta G can be found by using the delta G of formation that I mentioned earlier. Just take delta G formation of the product subtracted by those of reactants. Then you get delta G equal to minus 237 kilojoule. You can also say that this is formation reaction, therefore the delta G of reaction is supposed to be equal to delta G of water, delta G formation of water, which is this number. Okay? So if we apply this reaction in a fuel cell, the fuel cell looks like this. Okay? On one side you supply fuel, which is hydrogen in this case, and hydrogen would pass through the cells. This divider is basically an electrolyte, okay, that allows proton to pass through. If hydrogen is dissociated into electrons and protons, the proton move to the right hand side of the cell while the electron will be drawn away, and this electron can be used as our power. Okay, once it is used, electron would recombine with proton and oxygen, which is supplied on the other side of the fuel cell, and then the combination would give water. Okay, water is coming out. So even though in the fuel cell the mechanism of the reaction can be split into two halves, the anode part and cathode part, but if you look at the overall reaction is essentially hydrogen gas plus oxygen gas to get water. Okay, so if this fuel cell is operated at 25 degrees Celsius and 1 atm, then the maximum work associated with this flow of electrons can be calculated based on delta G of the whole system. So in this case it would be equal to minus 237 kilojoule per 1 mole of hydrogen gas supplied. Okay, if you find or if you calculate change in enthalpy or heat of reaction in this case, again this is formation reaction, this delta H will be the same as formation delta H of formation of water, which is minus 286 kilojoule. In this case, again, if you leave the reaction without extracting work, so let's say you have fuel cell but you don't connect the wire to your load, there's no electrons transfer out of the fuel cell. In that case, the system would release heat, 286 kilojoule as heat. Why did I say that? Because under the constant pressure, the heat released is equal to delta H, right? But if we extract electrons out of the fuel cell, the amount of work extract supposed to be equal to delta G, which is 237 kilojoule. And you can notice that these two numbers are not the same. If you extract it as heat, you get 286. If you extract as work, you can get only 237 kilojoule as work. The difference here is 49 kilojoule. What does it mean? Why can we extract all the energy as work? Okay, again you have to notice that now heat and work are not equivalent according to the second law. Let me keep this difference 49 kilojoule here as the blue letters. For this particular reaction, which was described in the part 1 of lecture 4b, during that time we calculate delta S to be minus 163 joule per Kelvin. And it is negative sign, that means the reaction itself does not have natural tendency to occur. But the process can be spontaneous only when the delta S of the universe is greater than 0, right? That means if you Find delta S of the universe from the delta S of the system plus delta S of surrounding. The system itself is negative sign, so therefore in order for the process to be spontaneous, the delta S of the surrounding must be greater than 163 joule per Kelvin. Okay, if it is greater than 163, that means process is going forward irreversibly. If it is 0, then process is spontaneous but it is reversible. So at minimum, in order to make the process work, or in order to conduct the process, you need to create delta S of the surrounding of 163 joule per Kelvin. That can be created only by releasing heat from the system to surrounding, create chaotic dispersion of energy in the surrounding. The amount of heat required would be temperature times delta S of surrounding, according to the definition, delta S equal to Q over T. Okay? So if I take delta S of surrounding to be 163 and assume that temperature of the surrounding is 25 degrees Celsius in thermal equilibrium with our system here, then we can calculate amount of heat required, and that would be 49 kilojoule. And you can see 49 kilojoule here in red and 49 kilojoule here in blue are exactly the same. What does it mean? Okay? So if you have the total amount of energy released from the reaction, this yellow area is amount of energy of the products subtracted by those of reactants. So this amount must be released because the process or the reaction is exothermic. 286 kilojoule must be released after the process takes place. 49 kilojoule is what is required to be released from the system to create chaotic dispersion in the surrounding so that the whole process becomes spontaneous. Without releasing this 49 kilojoule, the whole process will not take place from the first place. Okay? So this is the price that we have to pay so that we can make the reaction spontaneous. So if I release 49 kilojoule, that means the rest of the energy in the yellow part remains only 237. So I release this as heat to the surrounding to create enough chaotic movement so that the whole process becomes spontaneous. Once the process takes place, then the rest of the energy here can be chosen whether we would like to pick as work or as heat. If we like the rest of the energy to be transferred out of the system as work, then we can get 237 kilojoule as work. In this case, because it is fuel cell, the work will become non-expansion work. If we release the rest of 237 here as heat, this amount will be added to the 49 kilojoule that is already released as heat initially. So the total heat release will be 286 here as calculated from delta H. Okay? So if we extract as work, you got one certain number. As heat, you got another number. Again, heat and work are not equivalent. Alright? What we said for the Gibbs free energy usually are associated with the system with constant temperature and pressure. Now, what would happen if our system is not constant pressure? What would happen if our system is constant volume? We learned in lecture 2 that there are mostly two kinds of system that we consider, constant volume and constant pressure, right? If it is constant volume, then we cannot use Gibbs free energy that we defined earlier. We have to define a new way. Again, under the constant temperature and now constant volume assumption, the same thermal equilibrium assumption between system and surroundings still must be hold. Okay, T system is equal to T surrounding. Heat released from the surrounding should have the same magnitude as heat entering the system, or vice versa. In short, we can say that Q surrounding is negative of the Q of the system. And then at constant volume, heat released or heat enter the system is basically delta U of the system, right? From lecture 2. Then we can use the second law or definition of entropy change, delta S equal to Q over T, and Q here is delta U. Then we take delta S to be part of this delta S of the universe. Okay? That means we now can write the change in entropy of the universe as a function of system properties. But in this time, since the system is constant volume, we have delta U here instead of delta H we derived earlier for Gibbs free energy. Rearrange the equation and then define new variables called Helmholtz free energy, or A. Okay? A was defined as U minus Ts in similar manner as what we did for Gibbs free energy. At constant temperature, you can find delta A to be delta U subtracted by T delta S. Again, this T was moved out of the delta because it is under a constant temperature assumption. And you see that the right hand side of this equation is essentially delta A. So in other words, you can write delta S of the universe as function of delta A of the system. We don't need to consider about surrounding anymore. Okay, we can just calculate delta A of the system and use the second law right away. The question that some of you might ask. This minus T delta U minus T delta S of the universe was the same as what we did earlier. Okay? Oh, yeah. For spontaneous change, delta S of the universe is greater than 0, so you can use delta A smaller than 0 to determine whether the process is spontaneous or not. Okay? Again, earlier for Gibbs free energy, we got G equal to H minus Ts, and then at constant temperature you got this relationship and end up with delta G of the system equal to minus T delta S of the universe. These two are the same, are they? So does it mean that delta G and delta A are equal? You have to be very clear on this point. Even though the form of the equation are the same, but they were defined based on totally different system. Okay? For Gibbs free energy, this relationship was obtained under the system of constant temperature and constant pressure. But this equation was obtained from the system with under the assumption of constant volume. So these two are totally different systems. You cannot relate these two together. Okay? So just to be clear, a little bit clearer, for the system with constant volume, you can get delta A and you can get delta G of the system itself. Delta A of the system for this particular system of constant volume then would equal to minus T delta S universe. But delta G of the system of constant volume, you get the number, yes, but it has no meaning. Okay? So, delta A will be our tools for determination of the process spontaneity. So if delta A of the system is less than 0 or equal to 0, then the process will become spontaneous. Again, in similar manner, you can use delta A to calculate maximum non-expansion work that you can extract from the system of constant volume, in the same manner as what you did for Gibbs free energy. Okay, so these two are very similar in form, but when you use it, you need to pick whether the system is constant pressure or system is constant volume. But in chemical engineering application, most of the time the system would be constant pressure instead of constant volume, because normally we operate under the open system under constant pressure. Okay, And for instance, the phase change, the boiling of water, occurs at constant pressure. It does not occur at constant volume. So this relationship for Gibbs free energy will be used more frequently in thermodynamics, okay, especially in the next thermodynamics II, which consider mainly equilibrium of the phase. Then Gibbs free energy will be used throughout that course. So this is what we have for lecture 4B. Okay, for part 2 of lecture 4B, we focus mainly on Gibbs free energy, which is a foundation to be used later on in the next course of thermodynamics. So this is it for lecture 4B part 2. Thank you for watching.